Right now, a signal is crawling toward Earth from farther away than any human-made object has ever traveled, sent by a machine that is quietly running out of time. That machine is Voyager 2, launched in 1977 and still flying. In 2026, NASA is scheduled to permanently shut off another piece of it, the latest step in a countdown that ends with this spacecraft going silent forever. This isn't a hoax, and it isn't science fiction. It's a real engineering decision, happening in real time, and almost nobody outside of JPL is talking about it. Today we're breaking down exactly what's happening to Voyager 2, why its power is disappearing, what NASA is doing to fight it, and what actually happens the day the last transmission finally comes. No guessing, no dramatizing, just the facts, the engineering, and the real stakes. Drop a comment right now. If you could send one message into interstellar space, guaranteed no reply, ever, what would you say? I read every one of these, and if you want to catch every update on Voyager, deep space missions, and anything at the true edge of what humanity has touched, subscribe. It's free, and a like helps the algorithm find people who need to see this. Let's get to 5,000. Now, let's get into it. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1. Its original mission was supposed to last 5 years, fly past Jupiter and Saturn, take some photographs, measure some magnetic fields, and quietly end its working life somewhere in the outer solar system. Instead, Voyager 2 kept going. It became the only spacecraft in human history to fly past all 4 giant planets: Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. No other mission before or since has ever done that. Every close-up you've ever seen of Uranus's tilted blue-green surface, every image of Neptune's storms, came from this one spacecraft on this one uninterrupted flight. Then in December 2018, Voyager 2 crossed the heliopause, the boundary where the sun's solar wind finally gives way to the pressure of the galaxy itself, and entered interstellar space. It became only the second human-made object, after its twin, to leave the bubble the sun carves out of the galaxy. Today, Voyager 2 sits roughly 12.7 billion miles from Earth, moving away from us at close to 35,000 miles per hour. A radio signal traveling at the speed of light takes over 19 hours just to reach it. Send a command today, and you won't get confirmation for almost 2 full days. That record-breaking flight is exactly why NASA is fighting so hard to keep this spacecraft alive. Because right now, it's losing something it can never get back. Here's what most people get wrong about Voyager 2. It doesn't run on solar panels. This far from the sun, sunlight is thousands of times too weak to generate useful power. Instead, it carries a radioisotope thermoelectric generator, or RTG, a core of plutonium-238 that produces heat as it decays, which gets converted into electricity. At launch in 1977, that RTG produced about 470 watts, enough to run a handful of household appliances. But plutonium-238 decays on a fixed timeline nobody can slow down or reverse. Every year, without exception, Voyager 2 loses about 4 watts. Nothing is broken. Nothing has malfunctioned. It's simply physics, running exactly as it has since the moment the plutonium was manufactured, decades before the spacecraft left Earth. Do the math, and it gets brutal fast. Roughly 4 watts a year for 49 years means Voyager 2 has already lost more than 190 watts, well over a third of what it started with. It cannot be repaired. Nobody can fly out 12.7 billion miles to swap a battery. Whatever power is left is the only power this spacecraft will ever have again. Which is exactly why, since 2024, engineers at JPL have been doing something they openly call the hardest decisions of the mission: switching off instruments, one at a time, permanently, just to keep the antenna talking to Earth a little longer. Here's exactly where things stand. And the timeline is more dramatic than the headlines let on. Each Voyager originally carried 10 sets of science instruments. Most were built for the planetary flybys and switched off decades ago once their job was done. What's left are the instruments built to study interstellar space itself. In September 2024, engineers powered down Voyager 2's plasma science instrument. In March 2025, they shut off its low-energy charged particle instrument, a device that had run almost without interruption since 1977. Voyager 1 lost its own matching instruments on a nearly identical schedule. Now it's Voyager 2's turn again. In 2026, JPL is scheduled to shut down its cosmic ray subsystem, a set of telescopes that has measured high-energy particles for nearly half a century. Once that happens, Voyager 2 drops to just 2 working instruments out of an original 10. The same fate is scheduled for Voyager 1. Suzanne Dodd, the Voyager project manager at JPL, has been blunt about the timing. Her team's assessment was direct. Without action, the spacecraft would likely have had only a few more months of power before engineers had to declare the mission over completely. There is no backup plan here, no second chance. Once a switch is flipped 12.7 billion miles away, it stays flipped for the rest of the spacecraft's existence. But the scheduled shutdowns aren't even the closest call this mission has had. Something almost ended it early. And it wasn't on anyone's calendar. In February 2026, during a routine planned roll maneuver, Voyager 1's power levels unexpectedly dropped. This wasn't part of any scheduled shutdown. It was a warning sign. Engineers knew any further drop could trigger the spacecraft's undervoltage fault protection system, an automated safeguard that would begin shutting down onboard components on its own to protect the probe. That sounds like a safety net. It isn't. Recovering a spacecraft after an automatic fault shutdown at a distance where one message takes nearly a full day to arrive and a full day to confirm is an enormously risky process, one that could plausibly end with the spacecraft never fully recovering. So the team moved first, on their own terms, rather than risk losing control entirely. On April 17, 2026, they sent the command to permanently switch off Voyager 1's low-energy charged particle instrument, an instrument that had operated for almost 49 uninterrupted years. Kareem Badarudin, the Voyager mission manager at JPL, put it plainly. Shutting down a science instrument was nobody's first choice, but it was the best option they had. Every decision now carries the weight of possibly being the last one the team gets to make on their own terms. And there's one decision left that nobody has ever tried before. Engineers have one more move in the playbook, and it has an unsettling name. The Big Bang, a maneuver that would switch off an entire remaining set of powered devices all at once, rather than one instrument at a time. It's being tested first on Voyager 2, since it currently has slightly more power in reserve and sits closer to Earth, making it the safer spacecraft to experiment on. Nobody knows exactly how the spacecraft will respond the first time this is attempted. It has never been tried on any spacecraft this old or this far from home. If it goes wrong, the team could lose contact permanently, with no way to diagnose what happened and no way to send help. Even if everything goes right, there's a hard ceiling. NASA's own engineers believe both Voyager spacecraft could keep at least one instrument running into the 2030s, at best. Linda Spilker, the Voyager project scientist at JPL, has said it plainly. Every day the Voyagers spend exploring a region no spacecraft has ever reached could also be their last, even as it brings the chance of one more discovery. That's the entire mission now, condensed into one sentence. Every day is a bonus that could also be the end. It would be easy to treat this as a sad story about an old machine running low on batteries. That undersells what's actually at stake. Voyager 1 and Voyager 2 are, right now, the only two human-made objects in interstellar space. Not one of the thousands of satellites orbiting Earth, not the rovers on Mars, not anything launched in the last 30 years. Two machines, built with less onboard computing power than a modern calculator, are the only physical proof humanity has ever sent anything beyond the influence of our own star. Everything they still send back, magnetic fields, plasma waves, the boundary conditions of interstellar space, is data that cannot be collected any other way. No other spacecraft exists to replace them. No mission is scheduled to take their place once they go silent. If the Voyager 2 goes quiet tomorrow, that scientific window closes, and it doesn't reopen for anyone alive today. There's something else on board that has nothing to do with power budgets at all. Each Voyager carries a golden record, greetings in 55 languages, music from across human history, images of our planet, our biology, our cities. It was built assuming the spacecraft might travel for hundreds of millions of years, long after the sun itself has changed. The instruments will eventually stop. The transmitter will eventually go dark, likely sometime in the 2030s, once there's no longer enough power to even keep onboard electronics from freezing in the near absolute zero cold of deep space. But the spacecraft itself and the record it carries keeps moving regardless. Voyager 2 isn't going to fall or burn up or stop. It drifts outward forever, or close enough to forever that the word finally applies. So what does the actual ending look like? Not what you'd expect. Voyager isn't the first NASA spacecraft to face this exact ending. Its predecessors, Pioneer 10 and Pioneer 11, made the same journey outward decades earlier, and both went silent long before anyone was ready for it. Pioneer 11 stopped transmitting usable data in 1995, its power too weak to run both its instruments and its transmitter at once. Pioneer 10 held on longer, sending its last confirmed signal in January 2003, more than 30 years after launch, roughly 7.6 billion miles from Earth. Engineers listened for it for years afterward anyway, on the off chance a signal might still be there, too faint to confirm. None ever came. Nobody planned to send off for either spacecraft. There was no final message, no on-camera moment, nothing built for an audience. One day, the signal that had reliably shown up for decades simply didn't, and after enough silence, the mission was closed out on paper. That is the precedent Voyager 2 is now walking toward, on a longer timeline and with a much larger scientific legacy, riding on every extra year engineers can buy it. There will not be a dramatic final message. No last words, no countdown, no goodbye speech beamed back across the void. The most likely ending is quiet and procedural, the exact opposite of dramatic. At some point, power drops below the threshold needed to keep the transmitter and pointing systems running. Engineers send routine commands. For the first time in 50-plus years, the spacecraft doesn't respond. After enough failed attempts, the mission is formally declared over, not because anything catastrophic happened, but because the numbers simply ran out. That's the real final transmission. Not an event, but an absence. The last data packet from Voyager 2 will look exactly like every packet before it, right up until the moment they simply stop arriving. A question that comes up constantly whenever this story breaks. If Voyager 2 is this valuable, why doesn't NASA just launch a new probe to take over? The honest answer isn't about will, it's about time. Voyager 2 launched in 1977 and didn't cross the heliopause until December 2018, a 41-year journey made possible by a rare planetary alignment that let it use gravity assists from Jupiter, Saturn, Uranus, and Neptune to build up speed. Specific alignment happens roughly once every 175 years. It's the reason the Voyager missions were possible at all, and it's not available again on demand. Build a mission today without that same gravity assist advantage, and you're looking at decades just to reach the outer solar system, let alone interstellar space. No existing engine can make that trip meaningfully faster than Voyager 2 already has. In practical terms, whatever data these two spacecraft are still gathering can't be replaced on any timeline shorter than the lifespan of a small child alive today. It's also worth understanding how remarkable it is that either spacecraft can still communicate at all. Voyager 2's signal arrives at Earth measured in a fraction of a billionth of a watt, so faint that NASA's Deep Space Network has to be pointed with extraordinary precision just to detect it above the background noise of the universe. Every successful contact is, in a very real sense, a small technical miracle, repeated routinely, using a spacecraft pushed decades past what anyone who built it ever expected. Catching that signal isn't automatic either. NASA does it through the Deep Space Network, 3 giant antenna complexes spaced roughly 120 degrees apart around the globe. One in California, one in Spain, one in Australia. That spacing isn't decoration, it exists, so that as Earth rotates, at least one dish is always facing the right patch of sky, and Voyager 2 is never left talking to nobody. For Voyager 2 specifically, only one antenna on the planet is currently capable of sending it commands at all, a 230-foot dish in Australia, because of the specific angle Voyager 2's flight path took relative to Earth. In 2020, that dish went offline for upgrades for nearly a year, and for most of that stretch, NASA could still listen to Voyager 2, but could not talk back to it. If anything had gone wrong on board during that window, there would have been no way to intervene. That single point of failure is still true today. One antenna on one continent is the only line NASA has to send instructions to a spacecraft it has spent 49 years keeping alive. Every scheduled maintenance window on that dish is scheduled around Voyager's needs now, not the other way around. Nobody can stop the plutonium in Voyager 2's power core from decaying. Nobody can send it more fuel, more heaters, more capacity. Physics doesn't negotiate, no matter how historic the mission is. What the engineers at JPL do control is how much value they squeeze out of every remaining watt before the end arrives. Each instrument shutdown, each Big Bang test, each reluctant decision to sacrifice one measurement to save the rest, buys humanity's only working presence in interstellar space a few more months, a few more years. It isn't glamorous. From the outside, it looks like a slow, procedural decline. But it's also one of the most quietly disciplined engineering efforts happening anywhere on Earth, run by a small team keeping a 49-year-old machine alive across a gap so wide even light needs 19 hours to cross it. And when Voyager 2 finally goes silent, whether that's next year or sometime in the 2030s, it won't be the end of its journey. It'll be the end of the conversation. The spacecraft keeps moving outward, carrying its golden record long after everyone working to keep it alive today is gone. It is, quite literally, humanity's longest-running goodbye, still being sent one fading watt at a time. We'll keep tracking this as it develops. Every scheduled shutdown, every Big Bang test, every update out of JPL. Subscribe so you don't miss it. And leave that comment below. If you had one message to send into the dark, guaranteed never to get a reply, what would it be? This isn't just an engineering story, it's a human one. 5,000 likes on this one. Let's go. See you in the next one.